Okay, guys, go ahead and close your computers there. So here's the cool thing about physics. There's many cool things about physics, but here's one of them. We have some tools. We have figured out how to do a couple things. And now I want to show you how, without learning anything else new, we can use those tools to solve different problems, in particular projectile problems. So if you launch a cannon at a certain angle, how high does the cannonball go? How far does it go? Will you hit your neighbor with a water balloon? Those kinds of questions. We don't have to learn anything new to solve those. We have the tools. It's like, it takes woodworking classes. You learn how to use saws and hammers and nails and routers and things. And then all of a sudden, you reach the point where you can pretty much make anything you want. You don't have to keep learning. You can just start applying, right? In physics, there's a pretty small number of tools. So this unit, Unit 4, we're going to use some of the things we've learned in the past 3 units to solve interesting problems that don't require anything new, okay? There is no test on this unit. So I need you guys to just make me really high quality solutions in your notebook, because that's all I'm going to have to judge the quality of your work, all right? It's a short little unit. We'll be finished on Wednesday. I just want to kind of show you. I'm going to switch gears here. Put my cool little Mr. Large mask on. So we're going to talk about horizontally launched projectiles. All right. So that's the short little unit here. So let me kind of introduce it by talking about what a projectile is. So any object which is in motion and the only force on it is gravity, we say that object is a projectile. Okay? So if you take a ball and you drop it, after it leaves your hand, before it hits the ground, gravity is the only force on it. So we're ignoring air resistance. And if that's true, then it's a projectile. If I chuck it up, once I let it go, even though it's moving up, gravity is the only force on it, it's a projectile. And if I chuck it horizontally, so I throw it over there to Andrew, while it's in the air, it's a projectile. So I can throw it horizontally, or he can throw it back. Thank you. We can keep a little weight that way. It'd be kind of cool. So Bob? Sarah says no. By the way, ballistics is the study of projectiles. So that's kind of how we use our terminology. Ballistics is the study of projectiles. There's no such thing as ballistics is not the study of ballasts. Right? It's a little confusing there, but anyway. All right, so I'm going to show you a video. And this is because I can't do this because I don't have the stuff yet. But in another couple of years, I will have this gizmo. Neva, would you mind sliding the slider down on the lights there? So here's the video, and I'm going to kind of walk you through it. It's a silent video, so all you got's me. This is a guy named Alan, and he's going to set up a little demo here. He's got a vertical pole. He's going to attach it to the table right here. And he's going to make sure it's vertical using a level. There it is. Oh, good job. Now he's going to clamp this horizontal gizmo to it and make sure it's horizontal by measuring it there with the level. You adjust it a little bit. If you teach at the university, you just sign up and these guys come in and do the demo and leave. It's really cool. Now here's what happens. On the left side, there's a bolt, and he's going to put a ball on the end of the bolt so that when the bolt fires, the ball drops. Okay? On the other end, he's going to put a ball so that when the bolt fires, the ball gets knocked sideways. Okay? So now, what he's going to do is put a ball on one end. That ball on the left side is going to just fall, and the ball on the right side is going to get launched horizontally. Okay? So, when he flips the lever, the bolt's going to slide out. This ball is going to fall, and at the exact same time, this ball is going to get shot sideways. Which one's going to hit the ground first? The one going sideways? The one that's dropped? Or the same time? If you think the one going to the right is going to hit the ground first, stick up one finger. If you think the one that falls straight down hits the ground first, stick up 2 fingers. And if you think they're going to hit at the same time, stick up 3. Hold them up. Everybody's got to commit to something here. None of this. Come on, guess.
I did it before.
I didn't see. Hold it up. What do you got there, Chloe? 2? You think most of the class thinks the one that drops is going to hit first. So think about this in the extreme. What if it was a gun firing a bullet? If I fired a bullet sideways and dropped a bullet at the same time, which one would hit the ground first?
Depends on what you're shooting.
Doesn't depend on what I'm shooting. All right, so here goes. I'm going to slow it down. So here goes. Watch the ball's vertical motion. He's going to flip the lever. Bam. Which one hits the ground first? Oh, same time. They even bounce the same height. Look, the vertical position of the 2 balls is always the same. See that? It doesn't matter that that ball is moving sideways. It fell at the same rate. Okay? So, in the lecture, which I'll link online, you can actually see another movie. Mythbusters did this in a big warehouse with a big, long stretch of area and a bullet. And they actually dropped one bullet, shot a bullet, and showed which one hits the ground first. So you can watch that later in your own time. It's kind of a long video. So what I want to do now is connect to your lab. Okay? So let's talk about your lab for a minute. Let me get the lights again. So in lab, you guys did 4 parts, I think, right? So let's talk about those 4 parts from lab. In the first one, we had a marble rolling on a table and it fell off, right? And in part A, we graphed the horizontal position, the X position of the marble. And your graph looked like this. And I said, the question I asked was, can you tell from the graph where the marble left the table? Did anything change when it left the table? No. You can't tell. What it was doing up and down didn't affect what it was doing side to side. It was rolling on the table, rolling on the table, rolling on the table, and then it fell off, but the X position kept advancing the exact same rate. The other thing we can learn from this is that horizontally, the slope, which if you graph distance versus time, the slope is the velocity, the slope never changes. It's the same slope. That means it's the same velocity. So the acceleration is 0. Okay? Now, in the y direction, up and down, things were different. For a while, the y velocity was 0, which makes sense. It was on the table. It wasn't moving up or down, right? But then when it left the table, its velocity started getting bigger and bigger in the negative direction. And it started doing that, right? And if you found the slope using 2 points on this section, you got somewhere around -10, I think. From the ones I looked at, it was pretty close. Actually, this is Sarah's. Thanks, Sarah. What happened when you turned it in first? So, in the y direction, we found that it accelerated downwards at 9.8 meters per second squared, which is what it would have done if we would have just dropped it. The fact that it was moving sideways didn't change that. Okay? On the third one, we looked at the ball that was tossed. It went up and up and down and down. Can you tell where it's going up or going down? Nope. The motion vertically did not affect the motion horizontally. And lastly, the vertical velocity. The initial velocity vertically was positive. It was going up. Eventually it got to 0. That means it stopped going up, and then it starts coming down. But the slope of the line was always about -10. And you cannot ignore the intercept. It's clearly not 0, right? I'll just chuck the intercept away. So these 2 experiments that we did, plus the video, help us see the big important idea And that is that the horizontal motion of a projectile and the vertical motion are independent. One does not affect the other. Okay? That's the big idea that we're after. Okay, that's what we're going to kind of use to solve some problems. All right? Time connects the two, though. If I throw a ball, when it hits the ground, it stops moving vertically, and it stops moving horizontally if it sticks, right? We're not going to worry about what happens after it bounces. At least not yet. So that's what we're going to do. We're going to separate the vertical problem from the horizontal problem. It's a little confusing which way is horizontal. Point at the horizon. If somebody said, look, there's a ship on the horizon, which way would they be looking? Sideways, right? That's horizontal. Vertical is up and down. We use x for a horizontal variable. We're going to use y for a vertical variable, all right? All right, so if I fire a cannon off a cliff, and I fired at 20 meters per second, every second, the cannonball is going to go 20 meters sideways. And that will not change. Vertically, though, the velocity is going to increase. After 1 second, it's going to be going 10 meters per second downwards. After 2 seconds, it'll be going 20 meters per second downwards. After 3 seconds, it's going 30 meters per second downwards. And as you guys did in the warm-up, after 1 second, it will have fallen. See, without gravity, it would have been right there. It will have fallen 5 meters, right? That was the warm-up question. After 2 seconds, it would have fallen 20 meters. After 3 seconds, it would have fallen 45 meters. So it keeps falling farther and farther in the y direction while going the same distance in the x direction. That results in a parabolic trajectory or parabolic path. You move at a constant distance in the x direction and you keep moving in the y direction proportional to t squared, you get a parabola. Okay? All right, so here's the thing I want you to put in your toolbox. So grab your notebook, go to the back, make a new toolbox called Unit 6. No, Unit 4. Whoa. Sorry. I just skipped over a whole lot of fun. Unit 4 toolbox. And put this in it. A projectile is said to be horizontally launched if the initial vertical velocity is 0. Okay? Stick that in your toolbox. So, V is velocity. We're going to have a whole bunch of different velocities floating around, so we're going to use subscripts. Velocity vertically, we're going to use a subscript y. Velocity vertically at the beginning of the problem, we're going to use a little 0 after the y. So this means the velocity in the y direction at the beginning of the problem. Okay? All right. So what I'm going to do is model for you a problem. And we're going to solve it together, and you guys are going to do it on your paper because it's problem number 1 of your homework. So we're going to do problem number 1 of your homework together. You all get the same problem. So go back to the beginning, put problem set 4.1, question number 1. We're going to kind of do it together, and that'll leave you with the example to use. So the problem I've got is a marble rolling along Jared's table, and when it gets to the edge, oops, it hit his computer. Try again. Excuse me, sir. I got a marble rolling along Jared's table at about 1.3 meters per second, so about like that. And when it leaves his table, it becomes a projectile. It stops being a projectile when it hits the ground. And so I want to know how long is it in the air while it's flying off the table, and how far does it go horizontally? Where will it land? Okay? All right, so to do that, we're going to solve this problem. So the first thing we're going to make is a good diagram. Okay? Good diagrams come first. You don't add them later. Don't tell me I'll do that later. Start with a diagram. It's got to be bigger than your thumb, and it's got to have two things. You've got to show the path of the projectile. So maybe draw a table or something. But the table isn't what we care about. What we care about is the marble, when it leaves the table, it follows a parabola. So I want you to show me the path of the projectile, and I want you to show me what coordinate system you're using. Okay? We're using x's and y's, right? Where's 0? Is the coordinate, is that the origin? Is that the origin? Is that the origin? Is that the origin? You can solve the problem in any way you want, but you got to show me what you're using, otherwise your variable list doesn't make sense. So I am going to choose, to make my life easiest, the point that is right below the marble on the ground as my origin. Okay? That's going to be my reference system. And I want to see the reference system on your diagram. So for the diagram, I want to see the path of the projectile and the coordinate system you're using. Okay? Now, the next thing we're going to do is make a variable list. And your variable list might be a little bigger than usual. So if you want to make your variable list the width of your page and then solve below, you can. I'm going to keep them on the left and the right like I usually do. Okay? Guys, if you're not halfway through your notebook yet, you're going to be fine. I know a lot of you are squeezing things in tiny little lines because you don't want to, use up too much space. But make a nice big solution. Make it good. All right, here's our variable list. We are going to have two problems. We are going to have an x problem, and we are going to have a y problem. The x problem is what's going on horizontally. The y problem is what's going on vertically. And for each problem, we're going to have 5 variables. For the x problem, we're going to have delta x. We're going to have the velocity in the x direction initial, the velocity in the x direction final, the acceleration in the x, and the time. And those are all variables we've used before, back in Unit 1 and 2. The y problem is going to have the same set of variables, but for the vertical problem. We'll call that delta y. We'll have the velocity in the y direction initial, velocity in the y direction final, the acceleration in the y direction, and the time. And I realize it's a little tedious to write out 2 variable lists, but you'll live. You'll survive. I had a student a couple years ago who went home, and him and his crafty mom got together, and they made a stamp. You know those build-your-own stamp kits? They took tweezers, and they just glued on all the things they needed. So he had a variable list stamp. So he just stamp it on his page. I think he took longer making a stamp than it would have taken just to write it the 8 times he would have had to do it for the unit. But hey, it was cool. So if you're bored, go make yourself a variable list stamp. But there it is. Okay? Please notice we have subscripts for the x problem. We have a subscript of x on all of them, except delta x, because that's obvious it's x. Okay? All right, so now what we're going to do, once we make our variable list, is try to decode the problem. A marble is rolling along the table with a horizontal speed of 1.3 meters per second. What is the 1.3 meters per second? So, is it a velocity, an acceleration, or a distance? It's a velocity. Is it a horizontal velocity or a vertical velocity? It's horizontal, so it's v sub x. Is it the velocity at the beginning of the problem or the end? The beginning. So all of those things help us figure out that 1.3 is the velocity of the marble horizontally at the beginning of the problem. See how we got that? All right. It says the table is 0.763 meters high. I got that because I actually measured Jared's table. That's how tall it is, 0.763 meters. What is that? It's what? Delta y? Yep. It's 0.763 meters. Okay? And it's negative because the marble moves downwards, right? All right. What else do we know from this problem? Julia, Eli? Rock, paper, scissors. Loser has to give an answer.
I can try to read that, so.
Uh-oh. You need glasses? Julia, you got glasses. You read it. There's something else we know. Anybody? What? Go ahead. Look at your toolbox. What did you just write in your toolbox in Unit 4? If it's horizontally launched, what do we know? What's zero?
The velocity of line.
Yes. The initial velocity in the y direction is 0, and we know that because the problem tells us that it's horizontally launched. If the velocity at the beginning of the problem isn't 0, that means it's going either up or down, which is not horizontally launched. The word horizontally launched implies the initial velocity vertically is 0, okay? And that's why you put it in the toolbox. So if you see a problem that says horizontally launched, horizontal speed, that's the initial velocity in the y direction is 0. Okay, we need know 2 more things. Actually, a couple more things. 3 more things. Anybody? What else do we know? Yes, Laura. I thought your finger twitched.
I'm not sure. The acceleration in the y direction is 9.81.
Yes, the acceleration in the y direction is negative 9.81 meters per second squared. And we knew that from lab, right? What it's doing horizontally doesn't affect its vertical. It falls just as if it was falling. Delaney, did you have something?
That's what I was thinking.
All right, too bad. What else do we know? There's a couple more we know. What's the acceleration in the x direction? When we did the marble, was it speeding up or slowing down horizontally?
There was no change.
There was no change. So what's its acceleration?
0.
Right. There is no acceleration horizontally. Gravity does not affect the motion of the ball horizontally. That's why we couldn't tell when it left the table. But nothing changed about its horizontal motion. All right, we know one more thing. Natalie,
The final velocity of x is 0.
this is 0. The problem ends the instant before it hits the ground. So it's not 0. But we do know what it is. What's the final velocity in the x direction? How fast is it moving in the x direction? Yes, Eli.
1.3 meters per second.
How the heck do you know that? What?
The whole way through.
Yeah. The acceleration is 0. It never changes. The velocity in the x direction stays the same. So whatever is in the beginning, it's going to be in the end. You see that? There's a little irony. Eli saw it. All right, so that's our variable list. It's going to be the same every time. The acceleration of the x is always going to be 0, unless you choose to accept the bonus problem challenge, in which case we'll have a small negative acceleration due to air resistance. But for all of the regular problems, it's going to be 0. The acceleration in the y direction is always negative 9.81, as long as you're on Earth. Okay? You go to Mars and start throwing rocks, you got to start doing different calculations. But they're not that different. All right, so here's our solution strategy. This is a multi-step problem, and when you have a multi-step problem, guys, I want you to enumerate your solution. That means tell me what step 1 and step 2 and step 3 and step 4 are. All right? So step 1, we are going to solve the y problem. Delta y equals the velocity in the y direction initial times the time plus 1/2 the acceleration in the y direction times the time squared. You guys see that equation in your toolbox in Unit 1? Almost, right? I just put subscripts to keep track of which velocities and which accelerations I'm using. But that's the equation from Unit 1. It's the second equation we wrote down, right? We're going to solve this for t, because how long it's in the air depends only on how high it starts. Its sideways motion doesn't determine how long it's in the air. Whether you drop it or you shoot it sideways, how long it's in the air depends on how high it started. Okay? All right, so something 0 here, I can clobber it. What is it, Gus? Hey, Gus.
Yeah.
What's 0?
What's 0?
Excellent. The initial velocity in the y direction is 0, so we can clobber that term. You up, sleepy?
Just a little bit.
Stand up in the back there. It's okay. I don't care. We're trying to solve this for t. So, multiply both sides by 2. You get 2 delta y equals the acceleration of the y times t squared. I'm going to do 2 things, guys. I'm going to divide both sides by a and then take the square root. Is that okay? That tells me that t is going to equal 2 times delta y divided by the acceleration in the y direction, square root, and it could be plus or minus. That's my algebraic solution. Now let's plug in our numbers. Which solution are we going to keep, plus or minus? It's a time. The clock starts when it leaves the table. Obviously, it's going to hit the ground sometime later. We're going to keep the positive solution. So I'm going to just have the square root of 2 times negative 0.763 meters, all divided by negative 9.81 meters per second squared, and the square root of that mess. And so, grab your calculators. Let's see if we can agree here. Don't call it out. Let everybody have a chance to think about it. The first person who has it done calls it out. Everybody else checks out and doesn't do it. So, get it on your calculator screen. Jaden, what you got? Still working on it. Damon, you got it? No? All right, we're going to pick on Damon then. Actually, you know what? Damon, you ballpark it in your head. Then we'll take your answer first, and then Jaden will tell us the exact answer. Can you estimate that? Oh darn, now he's got to think. If you've got the answer in your calculator, just put it away. Can you estimate it?
Square root of like 0.15.
It's hard to take square roots of numbers less than 1, because they actually get bigger. All right, Jaden, what you got?
We were just doing the division part, right?
You're just doing this thing right here.
0.15
I think you forgot the square root.
Yeah, that's what I was asking you.
Oh yeah, do that.
Okay. 0.39. Do we do 3 significant figures?
2.
2? So then 0.39.
0.39 seconds. That's how, anybody else get that? Okay, that's how long the ball is in the air once it leaves Jared's table before it hits the ground. Okay? Now, we're going to use that number again, guys. So, either keep it on your calculator screen or store it. You guys know how to store numbers? You should probably have a lesson on that. I'll cue that up for tomorrow. Because this is actually an approximation, right? There's more to it. So, and we don't want to round when we use a calculation. So, let's keep that. All right, now here's the second step. We've solved the y problem for the time. We are now going to solve the x problem, which is delta x equals v0, the velocity in the x initial times the time, plus 1/2 the acceleration in the x times the time squared. We want to solve that for delta x. Technically, we're evaluating it because it's already solved, right? All right, JC, what can I clobber? Something zero there.
The acceleration.
Yeah, there is no acceleration horizontally. So this term goes away, which just tells us that the distance it goes horizontally is the initial velocity times the time. Horizontal. The initial velocity is 1.3 meters every second times 0.39 seconds. So take 1.3 times your previous answer, and you will have the distance it goes horizontally. Got that, Ethan?
Yep.
What is it?
0.51.
0.51 meters. That is what we call the range of the projectile. The range is the horizontal distance it goes. Let's think about it. If you're firing an artillery shell, the range is where you want it to land, right? You don't care how far it traveled up and over. You care how far from where you fired it, it lands. That's the horizontal distance. Okay? All right, so that's how we're going to solve the problems. Okay? When you solve the problem, if it's horizontally launched, the initial velocity in the y direction is 0. The acceleration is always negative g, and in the x direction it's 0. Fill in the rest, and this is a general template. The first couple problems, we're going to solve the y problem for the time, and then solve the x problem for the range. Okay? So you guys just solved problem number 1. So grab your computer, go to problem set 4.1. Question 1a asks for the time, so put in 0.39. Question 1b asks for the range, put in 0.51. And you just finished problem number 1. Now, go on. I want everybody to solve problem number 2. All right? Same solution structure, solve problem number 2 in problem set, and enter your answer when you get it done. And then once everybody got problem number 2, I'm going to go on and show you a slight variation. But I want you to practice this way first, okay? All right, we'll leave that up there.